In this video, we're going to take a look at functions. Now, before we can talk about a function, we're going to have to start with another term, a relation. A relation is a set of ordered pairs. A relation just ties two things together. And so, if we think about the ordered pairs we've been studying, they're the ordered pairs x comma y. So we've tied together these two elements. So for instance, we could have the point 1 comma 2. We could have the point 4 comma 5. Could have any number of points depending on what the relation tells us. And so, if we think about a line or a linear relation, those points would move evenly each time. So if we go up 3 on the x and the y is to go up 3, well then I would know the next point would be 7 comma 8. Both of them have gone up by 3s. Or we can see that the relation, the y value is simply 1 more than the x value. Now, it doesn't have to be that the relation is a linear set. It could be any sort of set. So it could just be a random set of 2 could go to 5, 3 could go to -7, 4 could go to 15. And I can't see any order to this, but for whatever reason, the relation is defined in such a way that 2 goes to 5, 3 goes to -7, so forth. Now, if we're to define these elements, in a relation, the domain is the set of initial values of the relation. And so we tend to think of these as the x's, the initial being the input. That's another good way to think about domain, the input. What do we start with? What is that initial? And then the range, the set of values in the second position, or the output of the relation. And we tend to think of these as y's when we have these ordered pairs, the input and the output, what we put in versus what we get out. Now, I've been using x's and y's here, but relations can tie any number of things together. It could be a person and their net worth. It could be that we're looking at maybe the inventory in a store, so we're looking at shirt type. So for instance, is it short sleeve, long sleeve, what have you, and its color. We could be looking at say a president and the number of years they're in office. Or the year that they're in office, or any number of things, right? So a relation is simply taking one set of objects to another. And so if I take that last one, right, the president and the years in office, just kind of working our way back in time, most recently we have President Trump, and he's been in office for 4 years, and we don't know if that'll go up or not, but currently that would be the relation between those two events. Obama we could look at, and we would have 8 there. And then we could look at W. Bush Jr. And he is in office for 8 years as well. And of course we'd have Clinton for 8. We'd have George W. Bush Sr., HW, and he would be only for 4, and then we have Reagan, and so forth. And so it just gives us this relationship between different events. And that finally brings us to our word function. So let's go ahead and define a function. A function is a special relation where every element in the domain corresponds to only one element in the range. Each element in the domain corresponds to only one element in the range. And so if I look at the relations I've defined so far to determine if they are functions, 1 goes to 2, it only goes to one spot. 4 goes to 5, only one spot. 7 goes to 8. Those are all only going to one spot. So this would also be a function. That one would check out. Here, 2 goes to 5, 3 goes to -7. 4 to 15. Again, every element in the domain is going to exactly one element in the range. And same thing here. Trump has exactly one output, 4. Obama has one output, 8. Bush has one output, 8. So let's look at something that is not a function, just to see what I'm talking about. So let's take a relation And I'll get back to my points for just a second. So let's say that this relation takes the value of 2 and turns into a 5, and then it takes the value of 3 and turns it into a 7. It takes the value of 5, turns it into 6. So far so good, but now I'm going to throw one in there. It also has the point 2, 4. Well, now we have a problem. 2 is going to 5, but at the same time it's trying to go to 4. I don't know where I'm supposed to go, and that's a problem. This would not be a function. So a good way to think about these is if I give you that input, that's what a function is doing. It's taking one thing to something else. It's taking an input and it's spitting out a result. It's like if you put a piece of metal into a machine and it turns it into a screw. That metal is your input, the machine is your function, the output is that screw. If I'm putting something in, I have to know what I'm going to get back out of it. I can't put in that metal and then one day get a pineapple out of it. That's not going to happen. That wouldn't be legitimate. That's not what the machine is built to do. And so if I put my 2 into this machine, I don't know if I'm going to get the 5 or the 4 because I don't have that clear answer. It's not a function. Or if I take a slight variation on the president example that we did just a second ago, I have that kind of flow chart of inputs and outputs. Let's say this time I put in an input, but this time it's not going to give me the number of years in office. It's going to give me a year that they're in office. So Trump, that one would go to 2020, the year that we're currently in. But it would also go to 2019. And so that's going to break on several fronts, 2018, 2017. And if we were to put in Obama, that would break on 8 fronts. It'd be going to 2009, 2010, all the way up until 2016. So there'd be several years there. And so this would be something that is not a function. So when we're thinking about functions and relations, we don't have to strictly think about x and y points. It could be words. It could be that example that we're dealing with categories. Another kind of fun function, we could take a letter and this function could make it a capital letter. So little a goes to big A, little b goes to big B, and so forth. So this would be a function because if I give you the letter Z, you know that that's going to have to go to the capital Z. You know exactly where it's going to go. And so if we have that clear, distinct path, that is fine. And so this example, it seems kind of silly, but this is kind of what computers do all the time. If you think about Word, it auto-corrects that first letter to be a capital letter. So there is coding in that computer. There's a function in that computer that says, hey, if this is in the first position, we need to change it over to this A. If this B is in this position, change it over. Let's take a look at another kind of goofy example, one that we wouldn't necessarily think of being a function, but is. So I'm going to build a function that takes a word and it removes the first letter. So apple, that would go to the letter A, and ball would go to B, and car would go to C, so forth. So then the question is this really a function? Because I can think of multiple words that would have a result of A. And the answer is yes, this is still a function. So sure, apple goes to A. So does all. Does that mean it's not a function? No, because I still know where that word's going to go. If I give you an input, if I give you any word in the dictionary, the answer D, you know exactly what the answer is. Now, that's not to say if I flip these things around that it's still a function. So if I try to reverse this example, so this time I'm going to start with the letter, and I want to build the word from there. A goes to what? Well, it goes to apple. But is that all? No, it goes to all. Is that all? No, it goes to anteater, it goes to aardvark, it goes to all these different things. And so this time, if I give you that letter and ask you to build a word, you don't know what the one correct answer is. In fact, there's a lot of different correct answers, a lot of different words that start with A. And so this is not a function. Even though before, when we reversed it, this was a function. This one is a function. If I take the letter example, if I were to reverse that one, if I were to start with the capital letter, A, well, this time I can reverse it. I know it's going to go to little a. If I were to start with big B, I know it's going to go to little b. So this one is reversible. So this reversible property, both of these being functions, this reversible property is going to be useful down the road. This is going to be something we call a one-to-one function, which we abbreviate 1-1, versus this is not a one-to-one function. Like I said, we're going to study this more down the road, but the idea is if I have a function, I start with something, I know exactly where it's going to go to. I can't have any uncertainty there. But if I have that function and I can reverse it, if I can go back the other direction, that is a one-to-one function. That's going to be a useful property because that's going to allow me to apply a function, but also undo that function. So if I give you the word apple and we go to A, you don't necessarily have that straight line bridge back across. I don't know if that A is supposed to go to apple, all aardvark, versus in the first example, A goes to big A goes back to little a. And so we're going to have that property to functions too. Now functions, we can look at points, we can look at these kind of bubble diagrams, we can also look at equations. So if we have an equation y equals 3x plus 1 and we ask ourselves, is this a function? This is a function. And so I'm going to think about it a couple of different ways. One way I can think about it is by thinking about those points. If I put in any value of x, how many y's am I going to get back out of it? If I plug in a 1 for x, I'm going to get 4. It's only one answer out of it. If I plug in a 5, I get 16. It's only one answer out of it. If I plug in 0, I get 1. One answer out of it. I don't care if those values ever repeat. The key is if I put in one value of x, how many y's am I going to get? Of course, only 1. If I multiply 3 by a number, it's still one number. If I add 1 to that number, it's still only one number. Versus, if I were to look at something like y is equal to plus or minus x. Well, now we have a problem. So we said before this function, this is a linear function, versus this one is not a function. And if we think about why this one is not a function, well, if I were to plug in 1 for x, I get two y values out of it. I get a positive one and I get a negative one. It tells me to have both the plus and the minus. So it's kind of weird to see an equation start off with that plus and minus. We don't tend to see that. We tend to see something maybe like y squared is equal to x. Y squared equals x. I don't know if this is a function or not because I can't see that y resulting from an x. I need to get that y by itself. So I'm going to start by taking the square root of both sides. And if I take the square root of both sides, I have to put a plus minus in front, which means y squared is really equivalent to y equals plus or minus square root of x. Well, now it's very obvious to us what we just talked about with that plus minus. This is not a function. So anytime you have that plus minus in front of the x and anything else going on with that x, it doesn't matter. If that plus minus is in front of it, it's not going to be functional. We're getting multiple values out of that one y. If we think about other radicals that could do that, or I should say other powers that did that, we started off here with the y squared. Well, if we think about the roots that are going to give us that plus minus feature, that's anytime we have an even root here. If we were to have y cubed equals x, well, if we want to get y by itself, we take the cubed root of both sides and we get the third root of x. Well, here we're back to a function. This is a function because if we plug in that one value of x, we don't have that plus minus in front. If we take odd roots, we don't put a plus minus in front. We just get the same sign. So the cubed root of -8 is -2. Only one answer. Cubed root of a positive 8 is +2. Only one answer. So anytime we're getting that plus and minus in front, that's going to be a problem as far as being a function. So I told you there's a couple ways we could think about these. We can think about them algebraically. We can also think about them graphically. So let me just sketch out a line real quickly here. This line is a function. If we think about why that is, every x has only one y. If I were to take this x value right here, I can see its y value is right here. Only the one y value. If I plug in x is equal to 2, whatever this y value, that is my answer. And so I have that one-to-one nature, I have that functional nature. It is also one-to-one. But it is a function because for every x, there is only one y. And so what I'm doing here is something called the vertical line test. I am mentally drawing a vertical line through every single point, or what I'm doing here with the dotted line. And if that dotted line only hits once, that dotted line is occurring at an x value. As long as I only see a y value once, that's perfect. That means it is a function. So for instance, something like the quadratic equation. Quadratic equation is a function. If I draw a dotted line, I'm only hitting that equation once. Even though it's getting very, very close to being vertical, quadratics are never vertical. And so this is a function. It doesn't matter that it's not unique. So for instance, here we see that this y value repeats. That's not what we're looking at. We're saying, hey, for every single x value, if I draw those vertical lines, do they only touch once? Yes, then it is a function. If I look at a circle, is this a function? No, it's not. I just hit twice, so this is not a function. And so even if you only hit twice at a single little area, for instance, if I have this graph, 99.999, in fact, infinitely many places, it's working out. It's just this one little area right in here that we're hitting a couple times, and so that's not a function. Something becomes vertical for just a second. So something like this stayed vertical in that short little period of time. That is not a function. If we think about even just having something that is a function, but then if there's a point sitting on top of it, that's now not a function because we are not passing the vertical line. That one single little point is ruining our vertical line test. So if I wanted to fix that, I could come in here and I could make this an open circle, because now I am saying I have a hole here. We get to that point, it's not included, and then the point's included up here. But as it was initially drawn, this is not a function. So even a single point can break that thing from being a function. So graphically, it's very easy to determine if a function is a function. And so if we know what something looks like, for instance, if we have f of x equals x cubed, and we remember what the shape of the x cubed function is, that would be a function. Or we could think about it in terms of the numbers. If I plug any number in for x, if I cube it, still only going to have one result. That is a function. And so functions we denote with this notation. Functions we write f of x. And there's a few reasons we would do this. This is read f of x, or a function f on x. And this gives us that direct relationship. We said that, hey, this x is the input, the domain and the independent variable, that's the input, and then we get something back out of it once the function acts on it. And so if I have an equation of a line, but I want to represent that as a function, say 3x plus 1, now I can see that direct relationship. I have an x value I can plug in, and that's going to give me a y value back out of it. So I could say find f of 2. And that would be saying, well, we need to plug 2 in for x. And when I do that, I see that I get a 7. So it's giving me that set of instructions. It's saying, hey, use this f function, but plug in the 2 and see what you get. Or we could say, using that same function, find f of 3. So I'm going to take the 3, I'm going to plug it in. 3 times 3 plus 1. Well, this time I'm going to get 10. So I can see that I'm supposed to be using that function. Why can't I just say, well, if y is equal to 3x plus 1, find what y is when x is equal to 2. I could do that, but that's a lot of words. If y is equal to this, what is y when y is equal to 3? Again, a lot of words. This is expressing that very concisely. Let's say I want to figure out what x is when y is something. I could also ask the question, find when f of x is equal to 2. Well, now I have that kind of what I've traditionally called the y, the thing over here, the y side. What is x when y is equal to 2? When or where is always talking about an x value. So what x value will give me a y value of 2? So I'm going to plug 2 in for the f of x side. I need to solve this equation, which means I need to subtract the 1. So 1 equals 3x. And then x would be equal to 1/3. Now there's a few other reasons that we use this function notation on top of it, just kind of being concise as we saw. What if I want to work with multiple functions at once? So what if I have function f of x defined as x squared minus 2, and function g of x defined as 9x plus 1? Well, if I just called both of these y's, I'd be pretty lost if I said find f of this and g of that. I wouldn't have a way to differentiate these two functions. So if, by calling them two different names, now I can say find f of 1 plus g of 2. I can work with both functions at the same time, and this is useful. There are many times in life that A scenario or a situation isn't dictated by just a single equation. Think about the weather. There's all sorts of variables, all sorts of equations that come into play with weather. So we might have a cold front coming through, but at the same time we might have a warm front sitting off the coast that's kind of pushing that cold front in a certain direction. So we have to have multiple equations playing into just one given scenario. So by naming these equations two different things, I can say, well, f of 1, well, that's talking about this equation here. I need to plug the 1 into that equation. But at the same time, so there's my f of 1 equation. At the same time, I need to add to that the g equation, but with 2 plugged in for the x. So here's my f equation with 1. Here's my g equation with the 2. So now I'm going to simplify. 1 squared minus 2 is negative 1. 9 times 2 is 18, plus 1 is 17. And so when I add those together, I get a grand total of 16. And so I can work with these multiple functions at the same time. I can work with as many functions as I want, in fact. So function notation, very convenient. Once we know that something is a function, gives us a nice way to name things. But the key to functions, we are starting with an input, we're plugging something in, and we're getting an answer out of it. That function is like a machine. It is taking it, and it is changing it in the ways that the function or the machine properties are dictating.